Welcome back everyone. In the last video, I introduced matrices and how they are connected to linear transformation. We have seen everything in detail. So if you haven't watched it, then I highly recommend watching it as it is important. Okay. Also, let me know in the comment if my volume is still low, as a few of you faced low volume issue in the previous videos. So I am right now fixing it, but if you are still facing the same issue, then I recommend using a headphone. All right. Okay. So we will begin with the non-square matrices. This lecture is about non-square matrices. I introduced matrices in my previous lecture. So before non-square matrices, I will just first give you a brief of uh, uh, square matrices. All right, square matrices. So just give me a minute. Yeah. So for example, uh, we have this input vector space uh, R2, right? This is an XY plane. All right. And let us suppose we apply a linear transformation, or whose corresponding matrix is A. And after applying the linear transformation, we are still in the same R2, that is XY plane. All right. So let us suppose this is the initial vector, and let us suppose this is the transform vector, which is A times V. Okay. So this linear transformation T is from R2 to R2, right? That is, this matrix A is transforming vectors from R2 to R2. So this A will be 2 by 2, right? So this is 2 by 2. A, B, C, and D. All right. So this basically means that we are this two here, the first two. This one is related to the vector coming from the input vector space, right? So this means that the input vector lies in R2. Okay, it is two-dimensional. All right. Whereas this 2 is this basically results in uh, this is related to the output vector space. Okay, so for example, our input vector lies in R2. So let us suppose it is this Vx and Vy. So after multiplying this with this matrix A, we will get the transformed vector. Let us suppose its name is Wx Wy. So this Wx Wy also belongs to, lies in R2. Okay, this lies in R2, and this is in the output vector space. All right, so if you see the square matrices are transforming vectors within the same dimensions, right? So either R2 to R2 or R3 to R3. Basically, the input vector, this V, lies in the same dimension as the output vector. So before the transformation, the input vector was lying in the xy plane R2 vector space. After transformation, it is still in the same vector space. All right, so I think this is clear. And as I already told you that this AC is where I hat lands, right? This is where I hat land after the transformation, and this is where J hat land after the transformation. So if you see, before the transformation, I hat was here and J hat was here. Basically, before the transformation, I hat and J hat both were in the in R2 only, in XY plane, right? right? And after the transformation, I hat and J hat, because they are still in R2, they have two coordinates AC and BD, so they are still in the uh, what you say, this is transformed I hat. They are still in R2, that is the same vector, same plane, the XY plane. All right. So this is very much clear. This makes sense. Then what is non-square matrices then? So for example, I will introduce non-square matrices. All right. So for example, I have this non-square matrix. Let us suppose this is 1, 2, 3, and 0, 1, and 2. Let us suppose this. So this is 3 cross 2, right? So first of all, I already told you that this is where I had landed, right? Where I had landed, and this is where J had landed, right? And this is also I already mentioned that this is the this is the dimension of the input vector space, right? So this is input vector space dimension. So basically it is 2. So the input vector is coming from R2, right? So it will have only uh, two dimension x and y, right? But the output is in R3 because this is 3, right? So if you see I hat, what is I hat? Before transformation, I hat is uh, 1 0 and J hat is 0 1, and both belongs to R2, right? This also belongs to R2. But after transformation, like transforming I hat with H, so this is matrix vector multiplication, right? So I am getting this 1 2 3, the first column. This belong to R3, and same goes for J. If I transform J hat using A, I am getting this 0 1 2, and this also belong to R3. So what is happening here? How is it possible? So this is possible because non-square matrices transforms vector across the dimension. So this is very important, that non-square matrices, non-square matrices transforms vectors across the dimensions. What I mean across the dimensions. So for example, this matrix A, for example, this matrix A, this is transforming a vector from R2 to R3. So A is transforming a vector from R2 to R3. So if I make the diagram, all right, so before the transformation, I hat is here and J hat is here, all right, in R2. But after the transformation, the output vector space is no more R2. The output vector space is 3D, R3. All right. So this is input vector space, which is R2, XY plane. All right. And this is output vector space, which is R3, that is XYZ space. Okay. So now I have transformed it, right? So this is 1 2 3. So I hat will go somewhere in 3D space. So if the maybe somewhere here, I mean, let's suppose this is in the 3D space, right? And J hat will be 1 comma 2. So x component is 0. If this is 0, so maybe this is the xy plane. So I hat will be J hat will be somewhere here. Okay. So if you see, you have moved these I hat and J hat, which were in the R2 space, the 2D XY plane, to R3 space, the 3D XYZ space, right? So how is it possible? It is done using the matrix A, because A is moving or transforming the vectors across the dimensions, because it is a non-square matrices. always remember that square matrices transform vectors within the same dimension. Here I mentioned it, right? That square matrices transform vector within the same dimension, right? But non-square matrices transform vectors across the dimension. This is important. All right. So, for example, what this matrix A is doing from R2 to R3, the matrix is transforming these basis vector I hat and J hat which belong to R2 to these transformed I hat J hat which belong to R3. So it transformed 2D vectors to 3D vectors. All right. But after the transformation, this 2D XY plane, right? This 2D XY plane will still be 2D plane, but in the 3D in R3 passing through origin, right? So it will be because we have just two vectors, right? Here we have two vectors, and two vectors can only construct a plane. It cannot construct a space, a 3D space. It cannot construct a volume. So how it will look like? So for example, after the transformation, this is the input xy plane. After the transformation A, after this transformation A, this space it will look something like this. I mean, this is going to be a plane. All right. Uh, okay. So this is the origin, and this is this transformed Li head, and this I would rather this is going to be A times I hat after transformation, and this is going to be this is A times J hat. All right, and make sure this passes through origin. Why? Because it's a subspace passes through origin. I will explain what are subspaces, but subspace is also a vector space. So it's a vector subspace, and all subspaces or all vector spaces always passes through origin. All right. So if you see before transformation also it was a 2D plane. This is XY plane, it's 2D plane. After transformation also it is a 2D plane, right? Before and after transformation it is a 2D plane, passes through origin, 2D subspace, right? So what is the difference then? The difference is now it's a 2D subspace within the 3D output vector space. So the output vector space is R cube, that is 3D. But this plane containing I hat and J hat, the transformed A I hat and J hat is still a plane because see, it's very intuitive, right? Two vectors cannot give you a volume. Two vectors always, if they are linearly independent, two linearly independent vectors always give a plane, always form R2. It can never form this thing, right? So the thing is, these two vectors ai hat and aj hat, although they are 3D vectors, because we have 3D vector because we have three components 1 2 3 0 1 2, right? But they still lie in a plane. If you try to create a plane passing through these two vectors, so they will lie in a plane. All right. Now the same thing goes for if instead of a if I have this matrix, let us suppose I have this matrix which is 2 comma 3. Okay, so let us suppose this is A1, A2, this is B1, B2, and this is uh, C1, C2, right? So this is where I had landed, this is where J had landed, and this is where K had landed, right? If that is the case, and this is 3, so that means that the input vector space from where the input vectors are coming is R cube, and the output is R2. Right? So what does this mean is that the input vector space, this matrix B 2 cross 3 is transforming vector from R3 to R2, right? That is transforming 3D vectors to 2D vectors. So kind of knocking down. So for example, initially this is the input vector space, and you have the vector lying in this 3D space belonging to R cube. Now let us suppose you have a transformation A times B, right? So now this, you can just imagine that you just knock down this vector v to this xy plane, to this R2. Now it will be somewhere, maybe somewhere here, let us suppose A times v, and this belongs to R2. So you see, non-square matrices are important because they transform vectors across dimensions. That's why they are important. That is their importance. Square matrices transform vector within the same dimension, whereas non-square matrices transform vector across the dimensions. So they are taking the vectors from one dimension to another dimension. That is like how beautiful it is. It is moving a vector from one dimension to another dimension, right? Okay. So one more thing I need to cover today is a very basic thing, is matrix multiplication. All right. So matrix multiplication is very similar to this linear transformation. If we apply consecutive linear transformation, how it behaves is same as applying consecutive matrices. So for example, uh, I have this vector xy into belonging to R2. Okay, I have this vector. Let us suppose this is v, which is equal to xy belonging to R2. Right. Let us suppose I apply this matrix 2 0 0 2. So what is this matrix doing? This is doing nothing, this, but it is just scaling the vector by the amount 2. And let us suppose this is matrix A. So what A times V is? A times V is nothing, it just scale the vector 2 times, right? This is A times V because I applied this matrix 2 0 0 2. That's all. Then let us suppose this will give me another vector, because matrix vector product is a vector. So let us suppose A times V is nothing but W, right? And then to W I apply another matrix, which is nothing but rotation matrix, 90-degree anti-clockwise rotation. And let us suppose this is B. So I did this B times W. So this will rotate the matrix 90-degree anti-clockwise. So this will be B times W, right? So if you see what I did, I applied two consecutive matrices to xy. So first I applied this matrix A, right, which is scaling by amount 2, and then I applied matrix B, which is anti-clockwise rotation by 90-degree. So this is B, A, and V. So I did this. So applying two consecutive matrices is same as if I multiply these two matrices and I transform this vector by that multiplied matrix. So for example, what will be B times A? B times A, what is this? This is nothing but 0 minus 2, 2 and 0. All right. And if you apply this matrix directly to V, you will get the same vector. Either you apply individually, you first transform vector V using A, then you transform the resultant vector W using matrix B, or what you can do, you can directly reach here. How? You can directly reach here. Let us suppose the matrix multiplication A, B, C. There, then you can directly apply C times V. That's all. So either you take this route, A times V, then B times W, you will get this, or you can directly come here, C times V. So you see that this is nothing. Basically, matrix multiplication is nothing but it is a composition of two transformation, right? So in this case, this is scaling and this is rotation. So what is the product? This is nothing but scaling plus rotation. So matrix product is nothing but composition of multiple consecutive transformations. So this is not restricted to just two. You can keep on adding the transformation, keep on multiplying matrices. It's like just composition of linear transformation. All right. I think it's very basic. I just want to touch it. So I explained it, but yeah. Okay, then few properties of matrices that I need to cover. Uh, matrix properties. Just two, three basic properties. The first one is that it's not commutative, that you have, sorry, that matrix A into B is not equal to matrix B into A. That is not commutative. It's not always. I mean, this thing is not always. It can be equal, but yeah, not always. Second is, if you have this A times B, then you multiply by C is equal to A, B, C. That is, it is associative. And third one is distributive. So it is also distributed. A, B plus C is same as AB plus AC. Distributive. All right. These are the three things. Apart from this, I will be covering. There are many special type of matrices, by the way. Nilpotent matrix, uh, the orthogonal matrix, idempotent matrix, and very important matrices and their properties. I will be covering them in the upcoming lectures. So that is this much only for this lecture. I just want to cover this non-square matrices. It has a very good visual interpretation, as non-square matrices moves vectors from one dimension to another dimension. Okay, so it can move a vector from sitting in R2 xy plane to a 10th dimension, and any dimension you can move from any dimension to any dimension, kind of a teleportation, but not teleportation, but yeah. So that's how it is beautiful. Okay, so yeah, I just want to keep this video short because it's very basic thing discussed here. Uh, yeah, in the next lecture, I will explain. Explain linear dependence and independence, because I will be covering few numericals on that, and it is important topic for GATE point of view as well. Okay, so if you like these lectures, if it is helping you, then please subscribe my channel, like my videos, share with other GATE aspirants or ML engineer with your friends, colleagues. Okay, thank you very much. See you next time. Bye.